Hey guys, good afternoon. Just getting the meeting rolling here, but welcome back everyone. Hope you all are well. And yeah, just about 90 seconds and then we'll really get things underway. Hey Jack, David, Jasmine, good afternoon everyone. Oh, well, it's close to the Spanish spelling, isn't it? Profesor. Not to worry though. It's been a good day so far, yes. Getting to the later portions of the semester, so it always starts to feel a little bit less stressful knowing that you've done most of the work already. Hi there guys, AJ, Angela, Annalie, Tina, Anthony, Moises. Peachy? Hey there guys. Just about 30 seconds. How's it going, Peachy? She's been hanging out with me today, so just saw her down there. Thought I'd pick her up for half a minute. Hi, Sylvia, Spencer, Alan. Okay. All right, guys, so it's 2:30. Let's get underway. Welcome back again, and thanks so much, as usual, for your attendance and for your contributions to these meetings. Do just take a moment to leave a comment at some point, and I'll just make sure to keep track of your attendance that way. Okay, so we just have another meeting today on this new topic that we started last time, which is time, the metaphysics of time and what to know about Einstein's theory of relativity. So I'm going to just kind of do a quick little brief review of Einstein's paper that we studied, and then we're going to try and go forward from there with the work of Ted Sider. And if we have a chance, maybe we'll even talk about some of the David Lewis paper today as well. So time is our current topic, and we're trying to get clear on what is time, what's the new modern day understanding of it that we have learned from Einstein, how is that different from the older classical view of it. So with Einstein, the paper in our book from 1916 is called Time and the Relativity of Simultaneity. So let's just try and review this and talk about it. The first thing he says is, suppose that there were these two lightning strikes that happened at two separate points on a railroad. If this was the railroad, let us say that these are the two lightning strikes, marked by positions A and B on the track. He says, suppose that the two lightning strikes happen simultaneously. It seems like that's a clear statement that everyone should be able to fully understand. But Einstein says it's not as easy to define the concept or to explain what it means as it sounds, because any attempt to define it will basically lead to circular definition. If you say that two events being simultaneous means they happen at the same time, this is not really anything other than saying the two events are simultaneous. So can we get a more substantial answer? And the way he puts it is that we should have some kind of method by which we could conduct a test, and the test could tell us whether or not the two events were simultaneous. So what's the way of testing the question? He says if we don't know how to do that, then maybe the concept doesn't have any real scientific meaning. So he says, let us think of this test. The test then would be to do the following. Measure the distance between A and B, designate the midpoint, which is the intermediate position between them, M, place a motionless observer standing still there at M. And this means that the distance between A and the observer is equal to the distance between B and the observer. If we assume that the speed of light is fixed, meaning that it never changes and that it's always constant and the same velocity from, say, A to M as from B to M, then if the person who's at that midpoint sees the two events in the same visual perception at the same moment, then we could claim that they were simultaneous relative to him. Because if they arrive at M at the same moment, and they've traveled the same length and they've moved at the same velocity, then that must mean that they departed from A and B at the same moment. So simultaneity then is defined as the receipt of two distant light signals reflected from the two different events that reach the given observer at the same moment of time. But given this definition of simultaneity, we can add another observer to the scenario, and for the second observer, the two same events won't be simultaneous. So suppose there was a traveler on a train, which is moving from left to right with constant velocity v, and they surpass the midpoint M along their route from left to right. Suppose that they intersect with the midpoint here at the same exact instant that this person conducts their own observation, and in this person's case, they see them as simultaneous. But since the first individual up here, person on the train, has velocity v, then they will not remain at M prime in the same way that this person will below. Instead, they're going to be continuously carried to the right with that velocity since the train is in constant motion. And that means that, unlike the first person, they will see the order of events in a different sequence. Can anybody remember which of the two lightning strikes will the second observer see first? Let me ask you that one, just to check with you for your comprehension and memory. Which of the two lightning strikes, A or B, is the first one seen by the moving observer who's going towards B and away from A as they pass the midpoint? Which one does the second guy in the train see first? Correct, Derek, it's B. That's right. And why is it B? Because now that the person is a moving observer, the same light rays that have to do some work to reach his eyes cannot possibly reach him at the same moment because he's closer in that case to B and further from the midpoint ahead of A. So that means that A, the light ray, is going to have to take additional time to meet his eye and less time for B since he's moving in that direction. So the same two events can no longer be claimed as objectively simultaneous. It does depend on the position and state of velocity of the given observer in comparison to other observers in space and time. Now, it's a weird result because it does imply very deep things. It implies that any two given events cannot be positioned in an objective linear sequence. Like you can't say objectively that any two events are ordered such that A is before B or after B or at the same time. It really just depends on where an observer is positioned relative to the events in space-time and their state of velocity compared to other observers. So it makes you think then that all the events of space-time equally exist. The things that you regard as happening in the future and them not having happened yet are relative to a different possible observer's standpoint, events that have already occurred. And so it's just so strange, and it really opens up deep thoughts about whether we even have the ability to have an open future. If this is true, then the future is just as closed as the past because all the events of all time, inclusive of the past and future, equally exist, and there's no priority given to the present. Let me add to this discussion with a couple of additional points about how the theory of relativity implies that time can change and the way that it passes can change depending on how fast or slow that you're moving. And good to see everyone. Hi there, Mia, Emily, Daniel, and all the rest. Appreciate your guys' attendance. Okay, so the next aspect of the relativity theory I want to go through is what's called time dilation. Now, time dilation can best be explained through the example of a light clock. We didn't talk about this light clock thing, I don't believe, last time. I think we just pretty much left it at the train example of Einstein. So this is all new. If not, you can let me know in the chat, but I'm pretty sure, according to my memory, that this is something we still have to talk about. So, okay. With this, let's assume that these are two planes of mirrored glass. This is the top surface and this is the bottom surface, so they both reflect light. As you guys know, mirrors, that's how they work. When you're standing in front of the mirror, light bounces off of your body towards the mirror. Since the mirror is a reflective surface, it just reflects the same image back, and that's why you see yourself in that mirror display. Now, let's take a photon of light, okay? Let's say that's a photon of light, and let's shoot it in the direction of the top mirror plate. Since this is a mirrored surface, it's going to reflect the photon beam straight back down. And because that's a mirrored surface itself, it'll reflect it back up. So now this becomes a time measurement device, and we're using the consistency of the speed of light to measure the passage of time. Let's assume that with each cycle of the light clock photon touching the top and bottom, let us suppose that that is a 1 second interval of time. So we have this bouncing photon between the two mirrored surfaces, And with each elapsed cycle of top to bottom, we count off 1 second, like on the clock. So now it is converted into something that can measure time. Okay, now, let's place an observer here with this light clock, who's standing still right next to it. And let us add a second light clock to the scenario up here. So here's light clock number 2. Now, with these 2 light clocks, let's suppose that they're perfectly synchronized, that they are in total synchronicity. So for each cycle of one, there's 1 cycle of the other, and they move in perfect unison. Maybe we even suggest that the 2 light clocks were issued from the assembly line of the light clock factory at the exact same time and date. So they're like twin light clocks, pretty much, and they measure time equally. But now, suppose that while this one stays in a state of rest, motionless, with this motionless observer standing by, we will then, at the same time, accelerate the top one while this one stands still. So this top light clock, we're going to accelerate it off to the right very, very fast with a high velocity, maybe even approaching the speed of light. Now, when the light clock is standing still and you're standing still with it, what is the arc of approach? What is the angle of approach for each photon cycle going up and down? Well, if you're standing still with the light clock and it's motionless also, you simply see a vertical path of motion. It goes straight up to the top surface, straight down to the bottom surface, and repeats. So if you're standing still and the light clock's right in front of you, you just see this, up, down, straight line, vertical line. But now what do you think would be the case for the motionless observer if he's looking at the top light clock as it accelerates quickly to the right? What will be the appearance of the angle that the photon takes as it takes its journey from the top to the bottom and completes each cycle? Okay, David, you say it's a wavelength. That's correct, yes. But in terms of angles and directional positions that a thing can take, what would be your way of describing the shape of the approach? You're basically onto it, but I was thinking of maybe one less technical way of saying it so that we can all kind of agree. Anyone else can say the same thing if they think they know what I'm suggesting. Just visualize it in your mind. It starts sliding off to the right, so it's not going to look like it's a vertical path. It's instead going to appear as though it is a more gradual path. And what does that, well, you say sine wave, Derek. Also, not necessarily incorrect. That's a good way to put it. But these are very heady ways of saying it. I think that it's a little bit maybe intimidating for those that are not versed in the science of sound waves or sine waves. So I was going to just say, can we all follow me here? A diagonal, okay? It's the same thing you're saying, but it's a little less intimidating. So a diagonal pathway. It's going to look as though a diagonal because given the velocity of the light clock, when you're standing still, it appears to traverse this trajectory because it takes longer for each cycle to be completed given the faster direction and amount of velocity that it has. So instead of this straight up and down path, you're going to see something like this. Think of it like this, guys, okay? If you're flipping a coin, let's suppose you flip a coin and it's just straight up and down flip. So it looks like vertical. Now let's put you in a car flipping the coin. If you're in the car, you just see it go straight up and down. But suppose that you were a person standing still outside of the car as the car drives past and the guy flips the coin. Well, what you would see is that it goes up, of course, as it departs from his thumb and going up, but it won't go straight up because there's horizontal acceleration in the car. It's a whole different frame of reference. So while you see it going up and the car going forward, it appears to be moving at a diagonal. And as the coin lands back in the person's thumb, you'd see it going down at a diagonal because you have a stationary state of motion and the other frame of reference is accelerating. So you'd see that gradual approach, unlike the person in the car who shares the state of motion with the frame of reference that they are in. So long story short, this then takes on the appearance to the motionless observer of a diagonal angle. Now, if that's the case, then after we've accelerated this top one several times, like let's say we allow it to orbit the Earth going at that high rate of speed multiple times, and then finally we reunite this light clock to a state of rest with its twin. So we allow it to come back, rest, and it's next to its twin again, and now they appear to be in synchronicity again. But here's the question. After that first one was, after the top one was accelerated and returned to rest with its twin, which of the two would have recorded more seconds? Do you think you can tell me this? Which of those two light clocks would have ticked off more cycles? The one which has the more gradual slope, or the one that's just going straight up and down? Which of the two will have elapsed more seconds after their reunion? The stationary one or the one that was moving? Hi, Isabella and Ismail. Good to see you guys. No worries about being late. Glad that you made it, though. But my question to all that are here is that. So we've taken the top light clock, accelerated it. Because of the acceleration state to the motionless observer, it appears to be taking an angled trajectory of approach. Now we allow it to come back to rest with its twin. And one of these two light clocks has counted more seconds now, because one was accelerated and one has stayed still. Which one has counted more seconds? Which one? You have two options. The one that remained still the whole time, or the one that was accelerated. Which one of the two, given the fact that this is taking a more gradual approach to complete one cycle, you can tell me, which of the two then would have shown more seconds, more cycles, in other words, of the photon beam going up to the top and then to the bottom? More cycles for which one? The one standing still or the one in motion?
Okay, so now we have a somewhat clearer sense of what science is. Let's talk a little bit about.
I mean, it's a clear answer, because if you're just looking at this diagram, one of the two scenarios, one of the two light clocks, involves a more gradual approach, and so that should tell you which one is going to take more time to complete a cycle. So of the two light clocks, after reunion, which one of them has accomplished more cycles of the light clock photon touching the top and bottom? Which one has ticked off more seconds? Okay, Alicia, I know that you're guessing, and same to you, Alan, because you both got the wrong answer. But it's okay. I like the fact that you at least were willing to hazard a guess. If I told you that it's the bottom one that has counted more seconds, you think you can reason your way as to why? Because I'm going to pains to show you that for the motionless observer, this one is going to appear to take a straight vertical approach. This one, because it's accelerated, depending on how fast it's accelerated, is going to have a more gradual diagonal approach. So this is just more space. The line segment is longer for it to complete one cycle than the space that it requires for this to just go top to bottom. So it is the bottom one that is going to count off more seconds. Why is the bottom one counting more seconds? Because relative to the motionless observer, who stays still with it, it is only going to have to go to the straight top direction and then straight bottom direction. It's not going to have to traverse this more gradual angled shape. So when one just has to go straight up and down, but the other one has to go like this to complete a cycle, this takes longer for one photon cycle to complete than this one does, because it's a longer length, since it's a stretched out wave, okay? So now here's the very weird implication that that has. It means that after the one clock was accelerated and the other one was at rest, when they return to a state of motionlessness and are reunited with each other, the bottom light clock has counted more seconds than the top one has, which means that the bottom light clock is actually older than the top light clock is, because more seconds have been recorded with respect to it than the other one. And so even though the two light clocks were issued from the assembly line at the same time, they're no longer the same age. This one is older than this one, because the fast-moving light clock has slowed down time relatively to other objects that are not moving as fast as it. So this is a very basic principle of the theory of relativity and the concept of space-time. The basic rule is this: when objects are moving and accelerating fast through space, they're moving through time slower relative to other observers that don't share the same state of velocity or motion. And this gives rise to a kind of interesting and puzzling phenomena of the theory of relativity, which is sometimes called the twins paradox. So let me just add to the discussion with this, the twins paradox. Just as I was saying before, that if you're in a car driving and you flip a coin, you don't see a diagonal, you see a straight up and down. But people outside of that same car, seeing you flip it, if they looked at you while they were standing still, would see the car whiz by and this diagonal approach for one cycle of the coin flip to accomplish. Now, suppose that we had two twin people. One of them is standing still with this light clock, and the other one is traveling with the top light clock, so they're riding along with it. Now, the two people are, say, identical twins, and I have triplets that are my siblings, so I know that, and you guys know, that when twins exist, human twins, they're the same age, basically. They're born at the same basic time, a couple minutes maybe separating the two, but they have the same birthday, etc. So twins are going through life at the same age. But suppose that we have one twin that we position on the moving light clock, which we then accelerate quickly. And we have the other twin standing still with the resting light clock. And they are also motionless with it. If we allow the top light clock with the other twin to accelerate very fast and then reunite it with its counterpart, now which of the two twins is older than the other one? Can you answer this one now? After the earlier discussion, I think it'll come to you sooner. But one twin was accelerated fast. One twin remained at rest. When we bring them back together, which one is older? The one that was accelerated or the one that stayed at rest? Which one's older? Now, the twin on the resting clock is now older. Correct, Alicia, for the same reason that your prior answer was incorrect, because when you thought the moving clock was the one that showed more time, it's the one that shows less time. So the stationary clock is the one that has more time recorded, so the stationary person with this clock is the one that has gone through more time than their counterpart. Now, how weird is that? Because this twin that would come back and meet up with their twin would see them years, months, however much older than them, depending on how long they were traveling at that velocity and how fast they were actually going. And that's such a revision of everyday common sense, because I know that you guys would think that if you have an identical twin, there's nothing that could ever happen that would make that twin and you different ages. But it's actually the case, and it would occur if we had the means by which and the technology by which we could accelerate human bodies closer to the speed of light. I don't know if any of you guys have ever seen or heard of the film Interstellar, but let me try and connect what I'm teaching you here to some of the science fiction themes of the film, because they're trying to employ some of the work of Einstein to make an interesting Hollywood movie. So in the movie, Matt McConaughey or whatever, he's like this interstellar astronaut who travels through space on these missions. And long story short, he has a daughter, and he goes out and accomplishes these various missions for the government, and he's flying around through space close to the speed of light. When he comes back and returns to Earth, one of the last scenes of the film, I hope it's not a spoiler alert, but one of the last scenes is that he's back on Earth now, and he's comforting his daughter who's on her deathbed. But his daughter is older than him, so she has leapfrogged him in age. She's now above him in age. She's an elderly woman, and he's still in his middle age. And why is that possible? Well, you would watch it, and if you didn't know enough about the science, you might just think, oh, weird stuff in movies. How does that happen? But it's actually an implication of the theory of relativity. If we did have such interstellar travelers that were moving that quick, then when they did return to Earth, they would return to a planet that had aged much more than the time that they spent relative to themselves on the space shuttle. So like a year or something out there traveling close to the speed of light could have been 5, 10, 20 years back home for everyone there, because of how much faster the person is moving than the people that are remaining at rest relatively on the surface of the Earth. So how strange is that? I know you would believe that if you had a daughter or son or anything, that there's no way that that person could eventually be older than you, leapfrog and get older than you. But this is actually what would be the case, in case we had the means at our disposal, again, to accelerate objects that fast. So that's like the concept of future time travel made real through the possibilities of the theory of relativity. Say we could put you into a centrifuge, and the centrifuge could spin close to the speed of light. Obviously, this is a type of situation that would probably make it impossible for you to survive, because those are physical forces that you couldn't really easily withstand. But suppose, for the sake of argument, that you could somehow survive being accelerated close to the speed of light in a centrifuge. When you enter into it and spin around at that speed, and then you get out, depending on how fast it was going and how long you were in it, the world that you emerged to would be much older than the amount of time that you spent in there. So like 10 minutes in the centrifuge could be 5 years, 10 years, whatever, into the future. And that's a real phenomenon. It's something that's been proven, actually. So we're in the intersection of science and philosophy at this point of the semester on the subject of time. And this is not all just metaphysical speculation from, the armchair position. This has been thoroughly tested and empirically verified. So one way to do that is to use particle accelerators that we have. So we cannot accelerate a human body with that much mass anywhere close to the speed of light. The fastest speeds that are achievable for a human body would be like getting in a space shuttle and going like thousands of miles per hour, multiple times beyond the speed of sound, but nowhere close to the speed of light, because the speed of light is 300,000 kilometers per second, or outside the metric system, 186,000 miles per second. So those are forces and speeds that we can't seem to accelerate big objects very close to. But what we can do is accelerate tiny little elementary particles over 90% of the speed of light in these particle accelerator chambers. And when we say take a muon, which is a particular type of elementary particle of the universe, and we accelerate it close to the speed of light in these chambers, it extends its half-life beyond what you would have had in case the particle had not been accelerated, and it perfectly matches the predicted results of the mathematical equations of the theory of relativity. Another case of testing the proposition before we had such sophisticated particle accelerators was to take two atomic clocks, place one of them in a fast-moving jet that goes several times the speed of sound, leave the other one motionless on the surface of the Earth, and when they return to reunion with each other, the fast-moving light clock has dilated time to an exact degree that was predicted by the mathematics of the theory of relativity. So even though much of this remains theoretical for our purposes, we can't practically invent the technology, it seems, to be able to achieve the time dilation effects for us. It's a real thing. Now here I have one more question about time dilation before I move on to the work of Ted Sider. So if time dilation is real, guys, meaning, again, that when you move through space fast, you have higher velocity, then you're passing through time slower than other observers who don't have the same state of velocity. If that's really the case, if it's real, and apparently it seems to be according to science, then how come we don't notice it? Why do you think that is? How come, for example, people who take a lot of flights, jet-setting type of people flying around, are not measurably aging slower than everyone else? Or why do you think it is that if I'm running around a lot of the time, I'm not having to reset my clock and synchronize it with everybody else who didn't go on a run? So if time dilation is true, then how come when people drive around the freeway, take flights on planes, go running, we don't see time dilate for them? It seems like we can't observe this effect in reality. If it's a real phenomenon, why do you think that it's not noticeable in everyday life? What would you say? Okay, good, Alicia, that's correct. It's because we cannot achieve not just the speed of light, but we can't achieve variable speeds that are anywhere close to that speed. So for the time dilation phenomena to be observable on anything other than a microscopic infinitesimal level, we would have to be able to achieve greatly divergent speeds, like you stay at a state of rest and I go accelerate like 100,000 miles per second. And since we can't achieve such variable speeds, the actual variable speeds that we can achieve make the time dilation effects infinitesimal and basically negligible. So the difference in the passage of time that I experience when I'm in a plane flying 600 miles per hour and you stay on the couch sitting still for the whole flight, the time dilation phenomena happens, but it's at such an infinitesimal level given that small divergence of velocity that it's not something that we could detect or notice. But if we actually did have the means by which to accelerate much closer to the speed of light while other people stayed at rest, then we would be all tied up in knots trying to synchronize our watches. Some people's watches would be running slower than other people's because we would be moving at such different velocities. Bounded on the surface of the Earth that we are, though, and limited with the technologies that we have, these time dilation effects remain marginal and mostly in the realm of the theory. Okay, but it's very interesting and weird stuff. So next up, though, we're going to continue on the same topic. I just wanted to add some more knowledge and detail to the initial presentation of Einstein. And now let's go ahead and talk about the work of Theodore Sider. Theodore Sider is an American philosopher, current-day working philosopher. He was born in 1967, and he's still doing a lot of good work. In the academy, in the profession, people call him Ted, but professionally, I guess, with publication, he goes by Theodore. So I know people that are like friends with him and stuff, and they call him Ted Sider. but it doesn't matter much to us. Okay, so in 2005, he wrote the article that we're about to look at, which is just called Time. So that's our current topic, to go through and explain Ted Sider's paper from 2005 called Time. Okay, so he begins by just saying that he wants to help us try and deal with some of the puzzling, paradoxical elements of the idea of time. Because what he notices is that when you start to investigate the idea of time below the surface depth and you try to really get into it, you start to notice that our everyday way of thinking about it breaks down and stops making sense. He notices that time is something that we just take for granted, that we don't usually investigate, like the air that we breathe. If you're a fish swimming in the water, you probably don't think, what is water? You know, you just live with it. We're surrounded by time, like the fish are surrounded by water, and we just take it for granted too. But he says we should take that extra step to try and analyze it. And one of the things that he thinks is so strange and hard to explain about it is this. So I'll put this on the board. He starts with this claim, and it's that time is puzzling. It's bizarre, puzzling, hard to explain because people say that time moves. Okay? Okay, so I just want to spend a moment here talking about the idea of time moving and how that seems to be a commonplace idea that people have. So can any of you guys think of common sayings or expressions that give voice to the idea that time somehow moves? I have a few in mind myself, but I'll throw it over to you to see if you have any on your end, that are familiar to you. So phrases, sayings, expressions, right, which say something about time moving. Okay, there you go, Catherine. That's a very well known one. Time flies. But to fly is a state of motion, like birds fly, airplanes fly through space. So saying that time flies is evoking the idea that time moves. But that's not the only such statement. There's time flies. Anybody know any other ones? There's a couple other ones. Time flies when you're having fun. I've heard that one, Alicia. Yeah, so they think that when you're enjoying yourself, time is just slipping through your fingers. I've heard people say when on the opposite side, that when they're very bored, oh, time is moving so slow. Time was moving so slow while I was waiting at the DMV. So moving slow is also a state of motion. And so that's another possibility. Sometimes people also have other examples of these sayings. There's time flies, time is moving slow. Have you ever heard people say anything else? A few others, maybe? Motion metaphors that are used when we talk about time. I've heard people say time marches on, okay, like time marches on. Time waits for no man, that's another saying. So marching, it's like a state of motion. It's not going to wait, it's going to keep going. People say time passes. Time is passing by. To pass by something would be to walk past it or to move past it in the spatial sense. People say time flows. Time is flowing. Like flowing is a motion metaphor as well, like how the river of water flows out. So whatever these sayings are, time flies, time passes, time is marching on, it's going fast, no, it's going slow. Well, what they all have in common is that they seem to indicate that when we think of time, if we think of it at all, we think of it as something that is moving and we're caught up in its movement. Anthony, I don't know about your example though. 15 Minutes of Fame just talks about the duration, doesn't necessarily say that it moved. Jasmine, there's no time to waste. Well, that talks about time as a quantity of something, but it doesn't necessarily talk about it moving either. So you got to use a word that has the motion as part of its meaning, like fly, run. People say time is running out, or time is running too fast. Running is a movement state. Flying is a movement state. Passing, marching. That's kind of what I was hinting at. But anyway, what these different statements indicate is that if anybody that's an everyday person like us, well, maybe, I don't know, if I'm an everyday person, I'm a philosopher, but anyway, everyday people think about time, they think about it as somehow some system that moves. But now we have a real problem to try and explain that, because ask yourself, what does it mean to say that time moves? This is quite difficult, if not impossible, to explain. And the reason he'll say is this. It's puzzling because motion itself depends on the concept of time to even have a definition. So let me write this here. This is puzzling because motion is defined with reference to time. So it's not easy to explain what it means to say time moves, because the idea of movement itself is defined with respect to time. So time is a necessary concept to even define what motion is. For example, let me try and demonstrate this. So here, there's this marker, and it's perched right here on this position of my table. And what's going to happen is the marker is going to move from this point, point A, to over here, resting next to this eraser. I don't know if you can actually see the eraser because it's kind of blocked, but let's say to the top surface of this pen case that I have. So here's A, here's B. I'm going to move the marker. Let me demonstrate. Okay, now the marker moved. Wow, it actually happened. Simple as it may seem to say that it moved, let's ask what it really means in detail. For marker to move from point A to point B, it has to be at different places at different what? Can you complete that statement? For anything to move, like for example, my hand that's moving from here to here, for something to move, it has to be at different places at different times. That's exactly right, Catherine and Alicia. If something is in the same place at all times, then that's the thing that's at rest and it's not moving. So right now I'm in this chair, you see, and if I stay in this chair for the rest of time, then I'll never move again. So for me to get up out of this chair and move, I'm going to have to be at some different place at a different time, okay? So motion is defined as an object being at different positions in space at different times. Therefore, if time moves, according to the definition we have, it would seem to go in a circle, because it would be like saying that time is moving because time is in different places at what? Different times. But now, if that's the analysis, it's circular, and it invites an infinite regress. Because how can time be in different places at different times? I mean, time is the thing that we're defining, so we cannot appeal to it in its own definition. That would be like somebody saying that, a square is anything that's a square. You can't use the word in its own definition because it fails to explain the concept. What you need is something that is the input to the definition, but the word cannot itself be part of the input. So that is why the concept of time moving is so deeply puzzling and troubling, because to move anything, it has to be in different places at different times, but time is itself time, so we can't really utilize the same definition and say time moves by being in different places at different times. To reinforce the point, there's a little graph and a description that the author has, so I'm going to talk to you now about that. So what we're going to show here is a graph that's depicted on the page 458. And what it's trying to show is it's a graph that depicts the motion of a train as it takes a journey from its starting point out of the station in Boston to its final destination a little down south in Washington, D.C. So to show the graph, we're going to draw 4 horizontal lines. And we're going to label these 4 lines with 4 time coordinates to the left. So this is lowercase letter t, and I'm going to have a subscript t sub 1, t sub 2, t sub 3, and t sub 4. Now that just means time 1, time 2, time 3, and time 4. And they're ordered in the order 1 through 4 because they're that's the temporal sequence. This is before 2, 2 is before 3, 3 is before 4. Okay. Now, let's say that we list the 4 place names that the train passes through on its journey. So underneath each of the 4 lines, we have these 4 city names listed. Boston, then it's New York, New York, Philadelphia, and finally Washington, D.C., the final destination. So we replicate that underneath each of the 4 horizontal lines here. Now, what we're going to now demonstrate is just the sequence of places that the train is if it moves starting from Boston to Washington, D.C. in the end. So initially, at the first time, when it's departing, it's out of Boston. It's in Boston. Later on, in the same sequence of events, it's no longer at Boston. At the second time afterwards, it's in New York. At a third subsequent time after that, it's in Philadelphia. And at a fourth and later time after that, it is finally to its destination, Washington, D.C. So looking at the graph, what you can see is this. How did the train accomplish motion from point A to point B? Well, by being in different places at these different times. If we change this graph and I edited it so that the train is Boston, 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 would that have been a moving train? Would that graph show the train moving? No. That graph would just show that the train stayed in Boston the whole time and never left the station. So it stays there all the time. Therefore, it didn't move. So again, as the graph hopefully makes vivid and clear, for an object to move through space, it has to be in different positions at different times. But how can this possibly work as a definition of the movement of time itself? If we say that time moves by being in different places at different times, again, we are defining the motion of time with reference to time itself. So time is moving with reference to time. This makes no sense. Objects move through space with respect to time. But if time moves with respect to time, what is this second order sort of time within which the first order time is moving? It seems that we would have to have a sense of hypertime. Time moves with respect to hypertime, but then that second order time has to be located in an even broader graph, and that leads to a third order sense of time on and on to infinity, and in the end we don't actually have any kind of non-circular analysis of the concept. So that's kind of led us nowhere, but he says maybe there's a different way to approach this. Let me read some of his words first, and I'll tell you about it. He says, it's strange to question the nature of time, given how fundamental it is to our experience. Ordinary objects move with respect to time. So if time itself moves, it must move with respect to some other sort of time. But what other time would that be? Examining the idea of time's motion or flow, what does it mean to say that a train moves? Simply that the train is located at one place at one moment in time, and at other places at later moments in time. See figure 1. This is figure 1 here. At time t1, the train is in Boston. At later times t2, 3, and 4, the train is located at places further south. The motion of the train is defined by reference to time. The train moves by being located at different places at different times. If at every moment the train stayed in the same place, Boston, then we would say that the train did not move. So plugging time into the analysis of motion's movement seems to lead us nowhere. So what's a better attempt? He says, okay, well, another way of looking at it may be that we try to explain the motion of time by saying it is the present moment that is moving. Maybe that's what we mean, yeah? So for time to move, it just means that the present moment, now, is always changing its position. Does this express the movement of time? Maybe it's a more viable attempt. Spoiler alert, though, ultimately he's going to say it doesn't work either. But let's go down that road and try and at least see the attempt. So can time move by the present moment moving? Okay, so here's a new graph that tries to give sense to this suggestion. 4 lines again. And we have these 4 time-like coordinates to the left. Now, suppose that instead of 4 place names under each bar, we draw 4 different times on the clock in a given day, starting with 12 noon. So noon will be the first, then 3 p.m., 6 p.m., and 9 p.m. Okay. So maybe by the statement that time moves, we mean the following. The present moment changes its position. So take a given day, like even today or tomorrow, whatever you want to use as your example. This morning when you woke up, I don't know if you're a late sleeper, if you're an early rise type of person, but whenever you woke up, that time of day, when you woke up, that was the now. At that moment, that point in time was present. Like you're like, this is happening now. But now at this time, earlier today when you woke up, what is the past? Okay, and now this is the present moment. Relative to my watch, it's about 3:13 p.m. on April 14th of 2021. So this is the current moment. This is now. Now think about 6 p.m. later today. Right now, that's the future. But fast forward to that time when it's going to happen, and at that point, then that will be the present moment, and this, what's happening now, will be the past, okay? And then later on, even after that, 9 p.m. will be the present moment when you're later on getting ready for bed or eating dinner or whatever you do. So the present moment, you might say, that's the thing that's moving. Earlier today, 12 noon was present. Right now, 3:13 is present. Later today, 6 p.m. will be present, and then after that, 9 p.m. So the graph would show this. Present starts off being at like noon. At a second later time, it's 3 p.m. that's present. At a further on time, 6 p.m. becomes the present moment. And then at a fourth and later time, it is 9 p.m. that will be the present moment. Now, does this help us understand or give an explanation of how time could move? Well, it's a noble attempt, but actually this also is not going to work. The author says there's something about this graph that's actually problematic. There's something on this graph that's sort of undefined. And I wonder if you have any guess that you could throw out there as to what it might be. Something on this graph does not yet have an explanation, and that's why it's not going to be fully explanatory. So what could be the problem with the graph that you see here? This graph, by the way, is also shown in the book on page 459. It's called Figure 2, the moving of the present moment. But what on this graph is yet to be fully explained? Anybody have a guess? Well, David, you're saying noon. If what you mean is that the times shown on the clock face don't necessarily correspond to any objective clocks in reality, I guess I could see what you mean, but not actually that. So nice attempt, but no. There is something else on the graph. Let me maybe, what's pushing it? A force. I like the idea there too, Derek, but it's not so much that, because that would be something that would go outside the scope of just what's written on the graph itself. Maybe I'll try to hint towards it a little bit to give you a little nudge in the right direction. What's up with the things here? What are these? What are these four things to the left? Can you tell me what those are? What do the things represent? The four designated terms, T1 through 4. Well, you say, Ishmael, that it represents time, right? But what the hell? I mean, I thought we were trying to define the movement of time independently. But it looks like in order for us to say that the present moment is moving, we're saying that it's moving by being in different places at these 4 different times. But what are these things? 1 through 4. It appears that they're moments of time that are ordered in a linear sequence. But how can they possibly be organized 1 through 4 unless they are time points which are located in an even bigger graph that has a third order sort of time which can organize these into the sequence 1 through 4. So these are undefined coordinates because they're time-like coordinates. We're trying to define time, but we're utilizing time itself once again to define what the present moment is moving with respect to. If we say the present moment is moving, what's it moving through? It's moving through these 4 times. But time itself is the thing to be analyzed, so it can't be part of the thing that appears in the graph. Therefore, you could say, Jasmine, those 4 timestamps are undefined. We can't help ourselves to a linear sequencing of time points if what is to be explained is how time could possibly have any movement or be sequenced. So once again, we've kind of run into a dead end. Trying to explain how time moves has just led us in a circle. We're saying time moves by being in different places at different times. So time is still undefined in that analysis. Well, Ishmael, you're saying time uses the definition of time, the definition of time uses time itself to be defined. That would be the problem, though. The author says that's not an accurate analysis because it's circular. So it begs the question, it's an infinite regress. So let me tell you what he actually then says is the better approach, Ishmael. He says, in the end, the best way for us to get around this problem is to just completely give up and say, you know what, never mind, time doesn't move. Time does not move. It doesn't move. All the events just exist. The past, the present, and the future, they're all there. None of them are starting. None of them are stopping. They are all there, and they're always all going to be there. And that's an implication of Einstein's space-time theory. So he says if we just make a full-bodied embrace of Einstein's theory, then we don't have to any longer deal with this problem because we just say it doesn't exist. If there's no such thing as time moving, then there's nothing to explain. And on the space-time theory of Einstein, that is an exact consequence. Because according to that theory, as I'm trying to explain to you, there's no such thing as the one moment that is the present. On the space-time theory, all the moments spread throughout all time, they're all equally real. So you sitting here right now at this particular point in time and space, the future parts of you, like you graduating from Fullerton, having kids, raising a family, having a career, getting retired later on, traveling and seeing things you haven't seen yet. All those future events on your timeline of existence, they exist. It's not just the present moment that exists. And all the things in the past behind you are also things that exist just as well. This is a result of Einstein's theory because, as you saw from the relativity of simultaneity example, that given a person's velocity and state of motion, the same two events could be seen as happening in an opposite order or even at the same time as each other, which means that there's no objective fact about what order they actually occur in, and therefore they're all equally granted reality. So it's a very weird picture to accept, but it actually is the consensus view of physicists and scientists today, as strange as it may seem. It's like sometimes called the block universe theory, where space and time don't move, they just hold all the events, and they all just sit there like one big block containing all of the past, present, and future as one. So that's the way he says that we should get around this problem. Say that time and space are integrated into space-time, and if that's true, then time doesn't move. Let me read what he says here. He says, time's motion has us all tangled up in knots. Maybe the problem is with that idea itself. According to philosophers and scientists, our ordinary conception of time as a flowing river is hopelessly confused, and it must be replaced with the space-time theory, according to which time is like space. Now, in contrast to the ordinary conception of moving or flowing time, the space-time theory says that reality consists of a single unified space-time which contains all of the past, present, and future. Okay, so now let me try and explain that by means of another diagram. Now you're being told that the space-time theory is the solution to this puzzle about how to explain time moving. But we want to then be able to fully comprehend what the space-time theory says. So how are we supposed to reconceptualize objects like ourselves according to the theory of space-time? Well, one way to see it is to draw what's called a space-time diagram. And one of these diagrams is shown on page 460. It's figure 4 in the book. So I'm going to draw one here on the board. Now, let's say this is our horizontal y-axis, and this is our vertical x-axis. Those are spatial dimensions. Now, this other line that runs through the intersection of the two of them, we're labeling it t because that's the time axis. That's the time dimension. Sometimes these are called four-dimensional graphs because in a perfect scenario, there would be three spatial dimensions, height, width, and depth. And then there would be the fourth dimension, which is time. Now, because I'm constrained to work with this two-dimensional board surface, I can't like show you like a pop-up diagram where it's got actually 3 dimensions of space with the time dimension running through them. So what you kind of have to imagine in your mind is that this is the typical flat horizontal axis of space. This is the vertical axis, and this is kind of running through their intersection, the time dimension there. Okay, now, to diagram the existence of an object on a space-time diagram, let me use the example of a human being. So, marked off on the time axis, let's show the year 2003. Right now it's 2021, and I'm thinking that some of you guys, because a lot of people who take this type of class are freshmen or underclassmen in college, some of you maybe have been born around that year, so I'm using it to make it relatable to you. Anyway, 2003, someone was born, and then let's say that they have a nice, long, happy life, like I hope you have, until 2100. So they made it almost to a full 100 years, 97 years old. Now, to show their existence stretched throughout time, I draw these little human-looking stick figures, okay? Okay, and then because the person dies, ceases to exist eventually, that's where the human shapes on the diagram cease. Okay, now, I have some questions about facts concerning the graph. Just give me your intuition as to why you think this is shown on the graph. Why do you think it is that I tried anyway to show the human figure here close to the beginning of the graph of 2003 as a smaller human figure than, let's say, somewhere later along the timeline. What do you think that is symbolizing or representing? Why, in other words, have I drawn such a small human shape here, whereas later it's a bit taller? What do you think the shortness along the x-axis represents at the beginning of the graph where it's 2003? Why so small there and then bigger later along the same t-axis? Okay, as a kid, right, exactly, guys, because when you're a very small child, you know, you have less mass, you're not as big. Look at your own childhood photos. It's an obvious fact that you have a smaller size. A baby that's born is what, 7, 9 pounds or something. Now you're a full-grown adult and you're much bigger. So that just shows the physical growth over time. Okay, so we have the sequence of little stick figure shapes gradually attaining a taller height, reaching like full maturity, and then that pretty much stays consistent through to the end. Now, another question about the graph. That was good. Why do you think that the graph shows this extension along the t-axis? What is that representing? So you told me that height on the x-axis and the variation that it has shows growth in size, in space, growth in space. But what about the extension along the t-axis? Why is that there? Why, for example, do we have this streak running from 03 to 100? What is that part representing? The amount of years, correct, Diego. So that shows the duration of time that the object exists. So on the time dimension, we show that the object exists for this period of time, for about 97 years. Now, in such a graph as this, the space-time diagram, we have to think and understand that objects have got both spatial and temporal parts. So the objects stretch in the other dimensions because of their spatial size, and they stretch along this t-axis because of their temporal duration, how much time they occupy in the universe. Now, on this conception of reality, objects, including us, have got both spatial and temporal parts. Now I need to define and explain to you what is a temporal part. Okay. So this is just a piece of terminology from the metaphysics and science of the theory of relativity. A temporal part is just an object at a single moment of time. Okay, an object at a single moment of time. So according to space-time theory, we have our spatial parts. Okay, now what are spatial parts first? Spatial parts are just the body parts of a human, or if it's not a human, then they're the different physical parts of an object. Take, for example, this chair that's right here. Well, I guess I can't really demonstrate. It's kind of out of view of the camera, but a chair has got different spatial parts. It has the legs of the chair. It has the back of the chair. I mean, I guess I could sort of demonstrate by means of the chair that I'm sitting in. You see, there's the back of the chair, there's the legs, there's the chair surface that you actually sit on. So those are its different spatial parts. If it was a car, I could say the wheels are some of the spatial parts, the trunk, the cabin, the hood, whatever. Okay, and in your case, your spatial parts, as you well know, are like your arms, legs, torso, head, and all of that. So the spatial parts are just the things that take up mass, that take up volume. So the reason that you occupy some range of space is because you have those spatial parts that are seated right now in your chair. That's the reason that other objects can't occupy the same chair right now, because your body occludes the space, it takes up the space, it crowds out the space that they could have used for that. Okay, so we all have spatial parts, and that's the reason that we have got mass and size. But we've also got on this theory temporal parts. And these temporal parts extend throughout our entire existence, and there's not just the one temporal part that we have in the present moment. So let's get deeper into this. A temporal part, as you see the definition, is simply an object, the whole object, but only at one instant moment of time. Okay? So let me try and get you to give me this answer so you can understand it. We all take pictures, right? I mean, we all have photographs, you know, sometimes on social media accounts we put posting pics. So anyway, you've got pictures and people take pictures. Suppose there's a picture that's been taken of a person, maybe you or someone else. It's a still frame photo. How many temporal parts of the person are shown in the picture? If it's a still frame, still image, how many temporal parts of the person are shown in that picture? There's a specific answer, and if you think about it, you should be able to tell me. So how many temporal parts do you think appear in a photo of somebody? Very good, it's one. Now, may I ask why you think it's 1? That's correct, but if you could just justify that so we can all understand where you're coming from. It's correct, but when the student explains it, I think that's helpful, and then I'll help you out to make it even clearer. So why would you say there's only 1 temporal part in the photo? Profile pic of you, 1 temporal part of you there. Why? Okay, David, you say because it's a still photo. Yes. And what is it about a still photo that makes it only have 1 temporal part? It's 1 instant of time. That's correct. Okay, good. And same, Alicia, because the picture was taken at 1 moment. It's a still photo, so it's not a video, right? The photo just captures 1 moment in the individual's existence. The light, that the camera device can captures that 1 instant of time. So that would be like 1 temporal part of you, the part that was displayed in the image. Now suppose that there was a little video that was taken of you. Maybe it's a short video, like one of those short TikTok videos or something, 15 seconds, I don't know. Question, how many temporal parts would be shown in a 15-second video of you? How many of your temporal parts appear in that little duration? Now this is a kind of trick question. To be fair, I know you really can't give a specific number, but like what kind of answer would you give? If I was to ask you how many temporal parts of a person are shown in a short 15-second video clip of them? In a way, there's a kind of formula for an answer. There are just as many temporal parts in the video as there are what in the video? What would you say about that? So we went with photo, now I'm going to video. How many temporal parts are shown of a person in a short video clip? Well, you say the number of seconds? Not quite, guys. Do you understand why I'm going to say no? Because the second is not the least interval of time that there possibly can be. There are half seconds, there are tenths of seconds, there are milliseconds. Now, Spencer, you're saying frames. And in the similar way, I have to push back on your suggestion too. Because frames have to do with the technological limitation on the recording device. As you guys know, frames differ from device to device. There can be some cameras that capture 27 frames per second, 30 frames per second, 60 frames per second. And then you can have super cameras that can do millions of frames per second. So it depends on the device. You have to think of this as like God's camera, okay? The absolute number of moments that there are, even if there was no human camera that could ever capture that many frames. Do you understand what I'm saying? So there would have to be just as many temporal parts of you in the video as there were, don't call them frames, as there are moments of time in that duration of time. Now, David, I was wondering if someone would put that out there, so now let me deal with your comment or question. You ask, is it infinite? Well, it wouldn't be quite infinite. It's a huge number. It's a huge magnitude of size in terms of how many temporal parts, because we all know that you can take a single second of time and subdivide it very, very far into tiny little nanoseconds. But why not infinite? Because if there was literally an infinite number of moments in even a short span of time, then that span would take forever, because even if each instant was extremely short-lived, with an infinity of them, you can't exhaust infinity. So it would make it appear as though a single moment could never end. But of course they do end. So instead of that infinite hypothesis, David, I would look at it like this. If you know a little bit about contemporary physics, there was a physicist named Max Planck. And Max Planck defined what is called the Planck Length. That's considered the minimum physical distance or length in the universe. So when you get to that length, you can't further subdivide it down into a smaller unit of space. And since space and time are unified on the space-time theory, we should expect for there to be a temporal equivalent of the Planck length with time. So there's a least minimal unit of time, and however very short that interval is, as many of those as there are in the video, that's how many temporal parts of you would be shown in the video. Okay, now, I'm going to keep asking you things about temporal parts to make sure this is sinking in. Right now you're watching this, and let me ask you this. How many temporal parts of you, or let me say it a different way. I don't want to ask in terms of a number. So there's a temporal part of you right now at 3:32 and 25 seconds p.m. Pacific Standard Time. Now, at this point in time, it's 3:32 and 33 seconds. Are those two temporal parts the same one? So like the temporal part of you that's responding to my question here, is it the same temporal part that sat down at the beginning of the lecture, or is it a different one? It's not the same one, correct, Alicia? So how come the temporal part of you that just typed that answer is a different temporal part than the one that is now hearing me speak? How come they're not the same? There's a reason, we can say it. How come each new moment there's a different temporal part? Well, I guess I'm saying it myself, because for each moment there's a different part in the sequence, and since time, contains these different moments, for each subsequent moment there's a different temporal part. So that kind of makes you think that you're not fully, well, let me ask this. According to the space-time theory, think about this question. Are you fully present right now as you hear me lecturing? Are you 100% present in your seat? Is the person that you are all there right now or not? Are you present or not present 100% while you're watching this lecture? I know that you've said you're present by tapping into the chat and leaving a comment, but it's a kind of deeper question. Are you fully present in the metaphysical sense as you watch this lecture? According to the space-time theory, are you fully present right now? It's a yes or no. Okay, and so David, you say no. Tell me why. That's good. Why is it that according to this theory that we are learning, you are not fully present right now as you watch this lecture? If not, then what is present? Why is it that you're not fully present? I mean, it's true, you're right, but I just kind of playing devil's advocate and ask you to, no, that's not it, Alicia. Although I like the idea and I see why you say that. It's a different reason. It has to do with the parts, the temporal parts that we're currently focused on. So you're not fully present as you watch this, because what is watching this? You're sitting in your seat, but what is that thing sitting in your seat during the time between 2:30 and 3:45? Is that the whole person that you are? No. According to the space-time theory, how much of you is watching this lecture? David, you said no. I thought you'd back up that comment with an explanation. Okay, because there are temporal parts that are later than the lecture, and there are temporal parts that are before the lecture also. That's all correct. Now, David, one thing I think that you don't understand, maybe because of the way you answered it, is you said because there are temporal parts from before the lecture. But there are also all the temporal parts of you that are after the lecture, because you need to understand that on the space-time theory, all of them are real. Not just the ones in the past and present, but the ones all out in the future too. So what's actually watching this lecture, guys, you, is not all of you. It's just a little tiny section of your temporal parts. So like the little cross-section that exists in the timeline of your existence between 2:30 and 3:45 p.m. on April the 14th. But that's just a little sliver of the temporal parts that you have. Because remember all those things that happened to you in your childhood and high school? Those temporal parts are part of your overall existence, but they're not here at this moment because that's in the past. And the future temporal parts of you that are done with this class and that are done with college and that are, retiring later in life, those future temporal parts are not part of this meeting either. So you also don't have access to all of me. I'm your professor, but you're only getting a few of my temporal parts, the temporal parts that are there at the times and dates listed on our syllabus. But you didn't see any of the temporal parts that I was a part of when I was coming up in college and graduate school and my earlier days as a professor. And you are not experiencing the temporal parts of me that happen after this semester is over either. So you're not fully present as you watch this. Some of your temporal parts are, but who is the whole person? The whole person that you are is the aggregate total of all the temporal parts summed up together, as sometimes metaphysicians call it, the space-time worm that you see on this diagram. The series of stages in the whole sequence overall, collected as one unit, that is the whole thing that you are. So you never, at a given moment of time, are fully present. Only one temporal part at a time is present. And so if you attend a lecture, some of your temporal parts watch the lecture, but others in the past and future don't. Okay? Hopefully that's now making some clear sense. Now, a temporal part is the same size physically as the whole body, but it's not the same size temporally. Now, because we endure through time and we exist for some amount of time, we're stretched out on the space-time diagram along that axis. If there was an object, like say a particle of antimatter, that erupted into the universe and it instantly annihilated itself, then it would only have a single slice on such a time-space diagram. You can think of a temporal part, as what some philosophers and scientists call a time slice of an object. So on this graph, you see how I draw this vertical line through it? Take that one instant of time that's marked off by the single vertical slash. That is like one instant in time, like one photographic moment of your existence. And that's just one of your temporal parts. you're the sum aggregate of all the temporal parts, and thankfully you have more than just one, and that accounts for the fact that you exist for a longer amount of time than just an instant. So on this view of the universe, reality consists of a single unified space-time which contains all of the past, present, and future, and you are an object that's stretched out not just through space but also through time. This requires us to disabuse ourselves of common sense notions like that the present is the only moment that exists. So you know all those kind of silly, I find somewhat annoying inspo quotes where it's like, seize the day, take charge of the moment, the now is all there is. The past is gone, the future hasn't happened yet. None of that is true according to this, because the future and the past both exist, and the present doesn't have any kind of special priority over them on the space-time theory. But it really spins off into weird and wild thoughts, like how can you possibly have free will? There's no open future then. The future is just as determined as the past, because all the moments exist. And really all you can do is observe them and watch them unfold, all the while with the illusion of your own free will. But the events of your future and past are all set forth by the laws of physics and the space-time reality that we're a part of, according to the theory anyway. So it's like we got rid of one problem. We don't have to explain how time moves anymore. It doesn't. It just sits there on this graph containing all the events of time-space with the 3 spatial dimensions, and nothing actually passes into being or goes out of being. There's no movement to time. There's just this big block of facts and events, and they're all sitting there. But it also is kind of strange, because now we have to reconceptualize our thinking about time and space in the light of the theory. So the last part from Ted Sider's article is to try and explain how to reconceptualize time after we learn about this theory and how time and space are much more similar to each other than we usually think. So he says there are 3 similarities between time and space according to the space-time theory. Okay, now I'll list these 3 similarities, and then I think we'll probably take a couple minutes at the beginning on Monday after we resume from the weekend to finalize this. But one of them is in terms of reality. Number 2, in terms of parts. And then 3rd is in terms of the words here and now. So if we're going to like have a full embrace of the theory of space-time from Einstein's work, then we have to grapple with the fact that according to it, space and time are more similar than we usually think in everyday life. Time is much more space-like than is sometimes conceived of. So these are the 3 points of similarity that we're going to mention. I have more detailed notes on this, but let me just at least speak about them a little bit informally, and then we'll be gone for the weekend. In terms of reality, so what this means is the following. No matter how close or how far an object is in space, it's still real. Okay, so like this marker right now is in front of my face, and it's real, and I can tell because it's right here. But it's not only real because it's close to me. It would be real if it was a little further from me, if it was a little further from me than that. What if I leave the marker here, and I leave my apartment, and I drive 30 miles away, and it stays on this book? Isn't it still real? Yes. So it's not only real when it's close up to me, the observer. It's real even when it's a mile away, 10 miles away, a million miles away. I could fire this thing off to the moon, leave it on the lunar surface, and it's not any less real because it's that far. So distance in space does not change how real something is. The claim here is that that's the same with events in time. So the present moment is not the only moment that exists either in reality. The past moments behind you and the future moments that you would consider to be out ahead of you, they're just as real as this present moment now. So when objects are present to you in space, like up close in your face, they exist. But when they're not present to you and they're at some remove spatially from you, they're still real. And the same is true of moments and the distance they have from us in time. This is the present moment, and it's certainly real, as I'm sure you agree. But according to the space-time theory, the beginning of this lecture that we already went through, that is real also. And it's not just like, oh, the video recording of it is real. No, like the body of me, the person, is still doing that lecture at that point in space-time because it's always been there and it'll always be there. And then the future time points, like say 20 years ahead, you watching, your kid get married or something, that future time point is also just as real as you attending this lecture right now. So in terms of reality, distance in space or in time does not affect at all how real something is. So that's kind of a weird and mind-bending thought, but grapple with it if you can. Like the future is real, it's out there. It's not something that's waiting to happen and it doesn't have any definite nature yet. All the events are just as real as this. And so the future is just as objectively like concrete as this right here. In terms of parts, the similarity is that objects take up space by having spatial parts, like hands, feet, legs, arms, etc. But also objects occupy time by having temporal parts. Okay, so temporal parts, that is the object at a single moment of time. The reason that things take up time in the universe is by having some of those temporal parts, and the more of them they have, the more time they endure through. So on either way of looking at it, parts, objects can take up space by having spatial parts or time by having the temporal parts, and they're equally real. When you look at your left hand right now, I'm sure you don't deny or disagree that it exists. And on the space-time theory, you're supposed to have the same kind of confidence that temporal parts of you located in the future and past relative to the current moment, they're just as real as your body parts are. So like your left hand exists, but so does you graduating in like a couple years, or you graduating high school in the past, last year, a couple years back. And then in terms of the words here and now, the last similarity that's mentioned. Well, I told you I'd run out of time a little bit, so that's something I'll have to save for the opening on Monday. But yeah, it's a fun and interesting topic, I think, to teach. It's right at the intersection of science and philosophy. It really kind of gives you a sense of the awe and wonder of the universe and our position within it. And it's really something that makes you think. It's food for thought. I was going to tell you a little bit more about the light clock scenario by means of the Doppler effect, because the Doppler effect is a real physical phenomenon that we experience with sound waves all the time. And it's exactly parallel to the explanation given of the light clock and why the moving light clock shows this greater diagonal angle of approach. Anyway, here's one word, just 2 seconds. When you're standing still and a car drives past you at a fast rate of speed, if that car's honking a horn, you're going to hear the pitch of the horn change as it approaches and as it drives off. Not just talking about the volume, but literally the frequency, high and low. As it comes up to you, because the distance between the moving object and your ear compresses the sound wave, it's got a higher amplitude and trough. And so that produces a higher pitched tone. As the same accelerating object of the car drives off away from you, it stretches out the sound wave because there's more distance between the moving object and your ear, so that creates a more gradual and stretched out amplitude and trough, which produces a lower tone. And that's why the stationary pedestrian, while the car drives past, hears this auditory phenomenon. If you're in the car and you share the state of velocity with the car, you just hear it's just no tonal variation. So the tonal variation is explained by means of one object being in motion while the other person is relatively at rest. And in the same sense, because photons of light are both particle and wave-like, they obey these wave-like properties when an object that's moving fast is emitting a photon of light to an observer. Okay, guys, so that's about it for now. Let me know that everything's good, and then we will conclude. I'll be sending off the essay prompts over the weekend, and we'll also speak about that on Monday. But for the time being, this is all I think I have for us on our Wednesday, the 14th. So how are you doing? Is it good? Okay, thanks, Alicia. I really appreciate your contributions today a lot, and everybody else. Don't want to close the stream too fast. Give you guys a chance to say your goodbyes. Okay, thanks, David, Nicholas, Annalie, everybody else. Again, if there's anything you need in the meantime, just be in touch with me, and I'll try to be as responsive as I can be. But other than that, keep your eyes on titanium announcements. I'll try to send the prompts in the next few days, and I'll see you back on Monday. If the space-time theory is correct, here's a little philosophy science joke, then you're already there watching it on Monday, and there's nothing you can do about it because you're locked into the sequence of events in your personal timeline. So I hope our destiny brings us together again on Monday, as I guess it already has so far. Okay, then, I'll see you soon. Bye-bye.